M&Ms race down conveyor belts as chocolate is coated, polished, and stamped with precision. Oreos roll through massive ovens, their wafers baked in perfect rows before being sandwiched with cream at lightning speed. Twizzlers twist and stretch through giant extruders, cut and cooled into uniform ropes of candy. Today, we take you inside the production lines to see the machines, the processes, and the non-stop rhythm that bring these iconic treats to life. First introduced in 1941 by Forrest Mars Sr., M&Ms were originally developed as a solution to a practical problem: how to make chocolate portable in hot climates without melting. Inspired by sugar-coated confections he observed during the Spanish Civil War, Mars created a candy-coated shell that would protect the chocolate core, making it suitable for military rations. Today, M&Ms are produced in enormous quantities across the globe in Mars Inc. factories located in the United States, Europe, Asia, and Australia. The most prominent facilities, like those in Hackettstown, New Jersey and Cleveland, Tennessee, run 24/7 to meet global demand, producing billions of individual candies each week. The process begins with the creation of the chocolate center. M&M's chocolate is a milk chocolate blend made from cocoa mass, cocoa butter, skim milk powder, sugar, lecithin, and flavorings like natural vanilla. The ingredients are mixed and refined on-site using 5-roll refiners that reduce the particle size of the chocolate mixture to below 20 microns, ensuring a smooth, creamy mouthfeel. This mixture is then transferred to large conching machines where it is kneaded, aerated, and heated for up to several hours to develop flavor and texture while evaporating any remaining moisture. Once the chocolate has been refined and conked, it undergoes tempering, a critical process that ensures the cocoa butter crystallizes in its most stable form. The tempered chocolate has a glossy finish, pleasant snap, and a higher resistance to melting and blooming. The chocolate is held in large jacketed tanks and piped to depositing equipment where the actual M and M centers are formed. These chocolate centers are not poured into mold trays like other candies. Instead, they are deposited into rotating spherical molds or formers that spin as they cool. This rotation helps round the chocolate into the smooth, lentil-like shape M&Ms are known for. The formed centers are cooled in large refrigerated holding bins and then screened to remove any misshapen pieces before proceeding to the next stage. At this point, the chocolate cores are dry, round, and smooth, ready for one of the most complex phases of the entire process: sugar panning. Sugar panning is a traditional confectionery process that has been transformed by Mars into a modern, high-speed, continuous operation. The chocolate centers are loaded into large, tilted stainless steel pans or draghi drums that rotate continuously. As the candies tumble, a fine sugar syrup is sprayed over them using automated nozzles. Each application adds a thin layer of sugar around the chocolate core. Between each application of syrup, the candies are dried using bursts of warm, dehumidified air, which causes the sugar layer to crystallize and harden. This process is repeated dozens of times, gradually building up the hard, crunchy shell that defines an M and M. The thickness and consistency of this shell is critical, not only for texture, but for durability during packaging, shipping, and vending machine dispensing. The sugar coating must be uniformly thick around each candy, and this is ensured by constant monitoring of pan speed, spray volume, air temperature, humidity, and dwell time. Each of these variables is controlled by a central processing system with real-time feedback from embedded sensors. Any variation in coating can cause breakage or visual inconsistencies, so panning operators use digital dashboards to maintain exact tolerances across the entire batch. Once the base sugar shell is complete, the M&Ms move on to the coloring stage. Here, food-grade colorants are applied through additional panning cycles, this time using either liquid or powdered dyes in highly controlled amounts. The colors: red, orange, yellow, green, blue, and brown, are applied in layers until each candy has a solid, opaque finish. Each color is run separately to prevent cross-contamination, and batches are blended later to ensure the correct mix is present in every bag. Following coloring, the candies are polished in large, slow-rotating pans with food-grade waxes such as carnauba wax. This glazing step gives M&Ms their signature shine and smooth feel. It also helps to seal the surface and improve flowability in packaging lines and vending machines. The polishing step is delicate. Too much wax results in a greasy feel, while too little produces a dull finish. Therefore, polishing is carefully time-controlled and monitored with visual inspection systems and gloss meters. Once polished, the final distinctive touch is added: the white M printed on each piece. This is achieved using high-speed industrial printers that utilize edible titanium dioxide-based ink. Each M&M passes under a laser positioning system that identifies the optimal printing location on the curved candy surface. A precise puff of ink is applied using stenciled or drop-on-demand printers, often operating at thousands of impressions per minute. Advanced vision systems inspect the print for legibility, alignment, and clarity. After printing, the candies are conveyed to the packaging line. M&Ms are sorted by weight and size using vibration-based grading tables, and then portioned using multi-head combination weighers. These weighers measure out the exact amount of product per package, whether it's a single-serving pouch, fun-size bag, or share-size tube, by comparing multiple load cells to achieve the closest match. Portioned candies are dropped into form-fill seal machines that create pouches from roll-fed packaging film. The film is printed with product information, branding, nutritional labels, and date codes. It is formed into a vertical tube, heat-sealed at the bottom, filled with M&Ms, then sealed and cut at the top. For rigid packaging, like tubes or boxes, vertical cartoning machines or flow wrappers are used instead. Each packaged unit is scanned for weight accuracy, seal integrity, barcode readability, and batch traceability. Packaging materials are designed for maximum barrier protection against moisture, oxygen, and light, all of which can degrade the chocolate and shell over time. Some packaging includes resealable zippers or tear notches for consumer convenience. Mars is increasingly investing in sustainable packaging innovations, including recyclable and compostable films that reduce plastic use while maintaining shelf life. Boxes of M&Ms are grouped into cases, loaded onto pallets using robotic palletizers and wrapped with stretch film for transport. Every pallet is barcoded and logged in the factory's warehouse management system, allowing full traceability back to every ingredient batch and process parameter. Finished pallets are either stored on-site in temperature-controlled warehouses or loaded onto trucks for distribution to retailers, vending networks, and international markets. Mars maintains strict quality and food safety standards at every step of the process. Facilities producing M&Ms are certified to international benchmarks such as FSSC 22000 and ISO 9001, with fully implemented HACCP plans and allergen controls. Metal detectors, X-ray scanners, and optical sorters are used inline to catch any contaminants or product defects. Each shift includes product sampling for texture, shell strength, gloss level, flavor consistency, and print alignment. From an environmental standpoint, Mars has invested heavily in making the M&M production process more sustainable. The company sources 100% certified cocoa for M&Ms through programs like Cocoa for Generations, which promote ethical labor and environmental conservation in farming communities. Peanuts used in variants like peanut M&Ms are sourced from sustainable agriculture partners. The factories themselves are moving toward zero waste to landfill operations, powered increasingly by renewable electricity and outfitted with high-efficiency HVAC and water recirculation systems. Digital technology underpins nearly every aspect of M&M production. PLCs, SCADA systems, and advanced analytics tools allow engineers to monitor every part of the line in real time. Predictive maintenance algorithms flag equipment wear before failure occurs, while IoT-connected machines provide granular data for continuous improvement initiatives. Some Mars facilities even employ digital twins of their production lines, virtual simulations that model physical operations to optimize throughput and reduce energy consumption. So the next time you pour out a handful of M&Ms, whether classic milk chocolate, peanut butter, crispy, caramel, pretzel, or fudge brownie, you're holding the result of one of the most meticulously engineered food production systems on the planet. What seems like a handful of colorful candy is in fact the output of multiple scientific disciplines: thermodynamics, food chemistry, robotics, optics, and packaging design, all working in concert to ensure that every single piece tastes and looks exactly as it should. Oreo, the world's best-selling cookie, is much more than a nostalgic treat dipped in milk. It is a precisely engineered product born from one of the most complex and refined food production systems in the world. With its iconic sandwich structure, 2 deep chocolate wafers encasing a smooth, vanilla-flavored creme filling, Oreo's success lies not just in its flavor and texture, but in the industrial mastery required to replicate that perfect balance billions of times per year in factories across the globe. First introduced by the National Biscuit Company in 1912, Oreos have evolved from a premium dessert biscuit into a global phenomenon produced in over 18 countries and distributed in more than 100. Owned today by Mondelez International, the Oreo brand is backed by a production infrastructure designed for precision, consistency, and speed, making use of the latest in food processing technology, high-capacity automated equipment, and rigorous quality assurance systems. Every component, the dark cocoa biscuit, the sweet white cream, the embossing, the snap, the twist, relies on deeply optimized processes that ensure every Oreo is unmistakably an Oreo. The Oreo production process begins with the base ingredients: flour, sugar, cocoa powder, leavening agents, salt emulsifiers, flavorings, and shortening. Each of these raw materials is received in bulk shipments and stored in dedicated silos, tanks, or controlled bins. Flour is typically stored in pneumatically filled silos made of stainless steel or aluminum and is delivered into the process through closed conveyor systems that prevent contamination and control humidity. Cocoa, a defining element of the cookie's unique dark profile, is specially treated to reach the signature Oreo color and flavor, often through a process called Dutch processing, which alkalizes the cocoa for a smoother, darker finish. In the mixing room, the chocolate cookie dough is prepared in massive horizontal mixers that can handle thousands of pounds per batch. These mixers are equipped with high-torque paddles and variable speed motors to ensure proper incorporation of ingredients, even distribution of moisture, and full development of dough structure. Water and fats are precisely metered in by flow controllers and load cells to achieve the correct dough consistency. Sensors within the mixers monitor dough temperature, moisture content, and density, sending real-time feedback to the factory's PLC systems. After mixing, the dough is conveyed to the forming area via chilled extrusion systems or dough feeders. The forming process uses rotary molder technology, a high-speed machine that consists of a rotating drum engraved with the Oreo's signature emboss pattern. The dough is pressed into these molds under pressure and then extracted onto a continuously moving steel belt. Each cookie is molded to an exact weight, diameter, and depth, with the intricate design on the surface providing both branding and structural rigidity. The embossing pattern, consistent across all global plants, is maintained using laser-engraved rollers that are regularly cleaned and replaced to avoid degradation. Once formed, the cookie pieces move into the baking tunnel, a high-efficiency, multi-zone convection oven stretching up to 100 feet in length. The cookies bake at temperatures ranging from 200 to 260 degrees Celsius for several minutes, depending on size and water content. The oven is divided into temperature-controlled zones that allow for a graduated bake. Early zones develop structure and lift. Middle zones bake through, and final zones help dry and crisp the biscuit. Exhaust systems remove steam and volatile compounds, ensuring even texture and color development. The baked wafers then pass through a cooling tunnel, a long conveyor system that uses ambient or conditioned air to gradually reduce the product temperature. This step is essential to avoid condensation, maintain crispness, and stabilize the cookie structure before creme application. Cooling time is calculated precisely to match line speed and ensure the cookies are ready for sandwiching. While the cookies cool, the creme filling is prepared in a separate system. The filling is a blend of powdered sugar, vegetable shortening, emulsifiers, flavoring, and sometimes stabilizers or milk solids. This mixture is heated and aerated in large jacketed tanks with high shear mixers to create a smooth, uniform paste. The texture must be just right, firm enough to hold shape under pressure, yet soft enough to spread cleanly and melt in the mouth. Color is monitored with inline optical sensors, and viscosity is measured in real time to keep the creme at ideal consistency. Once ready, the creme is pumped into depositor heads positioned over a moving belt carrying the bottom halves of the cookies. High-speed nozzles apply a precise dollop, typically 3 to 4 grams, of cream onto each cookie base. These depositors are timed down to milliseconds to match the movement of the belt and cookie spacing. As the creme is applied, the top cookie wafer is simultaneously placed on top using a vacuum pick-and-place mechanism or mechanical arms, sandwiching the cream and forming the completed Oreo. The freshly assembled Oreos then pass through a slight compression station where gentle rollers press the two halves together, evenly distributing the creme without causing overflow or breakage. At this stage, the cookies are carefully aligned to ensure the embossing is centered and upright, a detail that enhances visual appeal and brand identity. The sandwiched cookies now enter a final cooling phase to set the cream, ensuring that it re-solidifies and bonds with the cookies. From here, they move directly to packaging. The Oreo packaging line is a highly automated, high-throughput system capable of wrapping hundreds of cookies per minute. Cookies are stacked and aligned into trays, usually 3 to 5 per row, depending on SKU. These trays are conveyed to a horizontal flow wrapper that folds film around the tray, heat seals the ends, and prints the wrapper with production codes, batch numbers, and expiration dates. The film used in Oreo packaging is a specially designed laminate that combines durability with barrier properties to protect against moisture, oxygen, and light. Some packages feature resealable tabs applied during the wrapping process using pressure-sensitive adhesives. Vision systems check for alignment, seal integrity, print legibility, and barcode accuracy. Reject mechanisms automatically remove any package that fails inspection. From there, individual packages are grouped into multi-packs, shelf-ready trays, or export cartons using robotic cartoners and case packers. These secondary packages are then stacked and shrink-wrapped onto pallets by robotic palletizers. Each pallet is labeled and entered into the factory's warehouse management system, which links it back to every ingredient lot, shift operator, oven setting, and depositor head used during production. Food safety is paramount throughout Oreo manufacturing. Every ingredient and product is tracked through a digital MES with inline metal detectors, X-ray scanners, and moisture sensors guarding against contamination and deviations. Air quality is maintained through HEPA filtration, and line surfaces are sanitized using clean-in-place systems between production runs. All facilities are certified to international standards such as FSSC 22000 and ISO 9001, and allergen management protocols are enforced to separate dairy, soy, or gluten-containing variants. In terms of sustainability, Mondelez has invested heavily in making Oreo production more environmentally responsible. Cocoa is sourced through the Cocoa Life program, which supports fair labor and sustainable farming. Palm oil used in creme fillings is RSPO certified, and factories are increasingly powered by renewable energy. Waste heat from ovens is recaptured to preheat water or air in other parts of the plant, and zero waste to landfill goals have been achieved in many Oreo production sites worldwide. Digitalization also plays a crucial role in Oreo production. Sensors track every key process variable: dough viscosity, oven temperature, creme flow rate, cookie spacing, packaging line speed, and feed data into predictive models that help optimize performance and reduce waste. Operators use touchscreen interfaces to adjust machine parameters, and automated alarms help ensure immediate correction of any deviation. All this effort is what ensures that when you twist, lick, and dunk an Oreo anywhere in the world, you get exactly the experience you expect. The crisp snap of the cocoa wafer, the creamy sweetness of the filling, and the satisfying contrast between textures. This consistency is no accident. It is the outcome of a finely tuned, globally harmonized, and deeply engineered food production system that combines heritage with innovation. Twizzlers are produced by the Hershey Company, primarily at its state-of-the-art manufacturing facility in Lancaster, Pennsylvania. This plant has been producing Twizzlers for decades, and it now includes fully automated systems that can extrude thousands of pounds of licorice per hour. While there are several varieties, classic strawberry twists, pull-aparts, nibs, filled twists, and even black licorice, the production of the original twist-shaped candy is the foundation upon which all other variants are built. The industrial process begins with the raw ingredients. The primary components of a standard Twizzler include wheat flour, corn syrup, sugar, palm oil, glycerin, citric acid, artificial flavorings, and colorants such as Red 40. Each of these ingredients is stored in bulk silos, tanks, or food-grade intermediate containers. The wheat flour is particularly important. It provides structure and elasticity, acting as a starch-based matrix that can be stretched, extruded, and formed into consistent, rope-like strands. In the mixing phase, the dry and liquid ingredients are blended together in large, high-capacity industrial mixers. The mixing equipment used is typically a horizontal ribbon blender or paddle mixer capable of processing hundreds of kilograms per batch. The process begins by blending the wheat flour and sugar, then adding heated corn syrup, palm oil, glycerin, and water. The heated syrup helps to dissolve the sugar and hydrate the starch granules in the flour. Glycerin is added to retain moisture and preserve chewiness, while palm oil acts as a plasticizer that gives the final candy its smooth mouthfeel. Once the base mix is homogeneous, colorants and flavorings are added. Twizzlers' bright red hue and signature strawberry flavor are introduced in this stage, using FDA-approved food dyes and artificial or nature-identical flavor compounds. The mixture at this stage resembles a thick, dough-like mass that is warm, pliable, and highly viscous. Consistency is key. Too wet and the product will be sticky and difficult to extrude. Too dry and it will crack or deform in the next stages. From the mixing vessels, the warm candy mass is fed directly into extruders. This is the heart of the Twizzler production process. The extruder consists of a large screw housed in a heated barrel. As the screw rotates, it pushes the candy mixture forward while applying pressure and controlled heat. The combination of mechanical shear and temperature causes the starch and sugars to gelatinize and bind, giving Twizzlers their final, rubbery, elastic texture. At the end of the extruder, The material is forced through specially designed extrusion dies, steel plates with precisely shaped holes that define the cross-sectional shape of the candy. In the case of standard Twizzlers, the die includes a twisting mechanism that imparts the signature spiral ridges along the surface of each rope. For pull-aparts or filled Twizzlers, the dies are even more complex, sometimes including concentric extrusions that simultaneously produce an outer shell and an inner core of flavored paste. As the candy exits the die, it is still warm and malleable, so it must be immediately cooled and set. The extruded strands drop onto a continuously moving stainless steel or Teflon-coated cooling belt. Fans or refrigerated air is blown over the belts to bring the temperature of the strands down to a safe, stable level without forming condensation or sticky spots. The cooling process is carefully timed to ensure that the candy remains flexible but firm enough for cutting and packaging. Length control is another critical step in the line. As the cooled Twizzler ropes move along the belt, they pass through a guillotine cutter or rotary blade that chops them into exact lengths, typically between 6 and 8 inches, depending on the package format. These blades are driven by servo motors and synchronized with conveyor speeds using vision systems that detect rope spacing and ensure each cut is made in the correct place. The precision is such that each Twizzler stick in a package is virtually identical to its neighbors. Once cut, the Twizzlers are routed to the packaging area. Depending on the product variant, the ropes may be bundled, sorted into trays, or counted into specific quantities. For instance, a classic retail pack might contain 8, 16, or 32 sticks. These are grouped automatically using robotic pick-and-place systems that gently handle the candies using soft vacuum grippers or silicone tongs to prevent deformation. The grouped Twizzlers are deposited into form-fill-seal machines which wrap them in clear or printed plastic film. The film is formed into a tube around the candy, heat-sealed and cut, forming individual pouches or retail bags. All packaging is printed with production batch numbers, expiration dates, and traceability codes. These codes are linked directly to the factory's manufacturing execution system, which tracks every ingredient lot, processing parameter, and packaging run. This system enables full traceability in the event of a recall or quality issue, allowing the company to identify exactly when, where, and how each product was made. Before the packages are boxed and palletized, they pass through a series of quality control stations. Inline metal detectors check for any foreign material contamination. Weight sensors ensure that each package contains the correct number of sticks and proper weight. Vision systems use cameras and software to confirm that each piece meets color, shape, and surface standards. Any package or candy that fails to meet these standards is rejected automatically and rerouted for reprocessing or disposal. After final inspection, the packaged Twizzlers are loaded into display cartons or shipping cases using robotic case packers. These boxes are labeled with scannable barcodes, sealed, and sent to palletizing robots. The pallets are shrink-wrapped, labeled again, and moved into climate-controlled storage areas until they are ready for distribution to retailers, vending networks, and export partners. Throughout the entire production cycle, food safety and hygiene are tightly controlled. All processing zones operate under strict HACCP protocols and are regularly audited to meet global food safety standards such as SQF and FSSC 22000. The plant is divided into zones to manage allergens, cleaning protocols, and personnel movement. Production equipment is sanitized using clean-in-place systems, and the entire air handling system uses HEPA filtration to reduce microbial load. Sustainability has also become a growing focus for Twizzlers production. Hershey has committed to reducing water usage, cutting greenhouse gas emissions, and sourcing ingredients responsibly. Palm oil used in Twizzlers is RSPO certified, and packaging films are being redesigned in many markets to be recyclable or made from recycled content. Factory energy systems are increasingly powered by renewable electricity or supported by waste heat recovery systems that improve overall plant efficiency. Digitization is another pillar of Twizzlers' modern manufacturing. All process equipment, from the extruders and cutters to the cooling conveyors and packaging lines, is controlled by PLCs with networked SCADA systems. These systems allow real-time monitoring and control of temperature, moisture levels, extrusion pressure, conveyor speeds, and even candy color. Predictive maintenance algorithms monitor vibration, wear, and energy use to prevent downtime. Operators use touchscreen panels and digital dashboards to keep production running at maximum efficiency. So when you tear open a pack of Twizzlers and enjoy that glossy, flexible, chewy rope of candy, you're not just tasting a snack. You're holding the result of decades of engineering innovation, food science, and process optimization. What seems like a simple candy is, in reality, a masterfully controlled product of extrusion technology, thermal regulation, moisture balance, and automated quality assurance. Each Twizzler is manufactured with more precision than most consumers realize. The spiral ridges, the sheen of the surface, the even chewiness from end to end, all are the result of controlled variables in pressure, temperature, and time, executed at industrial speed and volume. Twizzlers are not just a fun treat. They're an edible product of engineering excellence, designed to deliver consistency, shelf life, and sensory enjoyment in every single twist. To understand how Takis are made in a factory, we must begin at the very first stage, the sourcing of raw materials. The cornerstone ingredient in Takis is corn, more specifically, degermed corn flour, often referred to as mesa flour. This flour is derived from yellow or white field corn, grown primarily in the United States and Mexico. The corn used must meet specific quality parameters, particularly in terms of kernel size, moisture content, and starch composition. Contracted farmers typically grow this corn under strict agronomic practices to ensure high yield and consistent quality. Once harvested, the corn is transported to centralized milling facilities, where it undergoes a critical transformation. This transformation begins with the nixtamalization process, a traditional method that dates back to ancient Mesoamerican civilizations. In modern milling operations, dried corn kernels are steeped in a lime water solution, water mixed with food-grade calcium hydroxide at controlled temperatures for several hours. This chemical soaking loosens the hulls, softens the kernels, and alters the protein and carbohydrate structures, improving both flavor and digestibility. Once steeped, the corn is thoroughly washed to remove residual lime and loosen pericarp. What remains is nixtamalized corn, which is then ground through industrial stone mills or hammer mills into a fine, homogeneous masa dough. For Takis, however, the mesa is taken one step further. Instead of being used wet, as in tortilla production, it is dried and ground again into a shelf-stable mesa flour. This dried masa, now fine and moisture-free, serves as the primary input in the Takis production process. It's stored in massive silos within the factory, equipped with aeration systems to keep the flour dry and flowing freely. Pneumatic conveyors transfer the flour to precise metering hoppers above the mixing equipment. Here is where the transformation from flour to snack begins in earnest. The masa flour is dropped into high-capacity industrial mixers, where it is blended with water and a proprietary mixture of seasonings, emulsifiers, and sometimes oil. These mixers are equipped with temperature control systems and paddles designed to evenly distribute moisture throughout the blend. The goal is to create a pliable yet firm dough that is suitable for extrusion, a process that will ultimately define the iconic Takis shape. The mixed dough is conveyed directly to the extruder, a high-pressure, high-temperature piece of equipment that lies at the heart of many snack food manufacturing lines. For Takis, a twin-screw extruder is typically used. The dough is fed into the extruder barrel, where rotating screws push the material forward while simultaneously mixing, shearing, and heating it. Inside the barrel, steam pressure rises dramatically due to intense friction and controlled moisture. This heat gelatinizes the starches within the mesa, turning the dough into a malleable, semi-cooked matrix. At the end of the extruder barrel lies a die plate with specially engineered openings. These dies are shaped to produce flat ribbons of mesa with uniform width and thickness. As the dough exits the extruder, it experiences a sudden drop in pressure, causing it to puff slightly, though not excessively, as Takis are denser and more compact than puffy snacks like cheese curls. Automated blades then cut the ribbons to a standardized length, usually between 4 and 6 inches. Now comes one of the most recognizable steps in the process, the rolling. Using a synchronized series of mechanical arms and belt-driven rollers, each flat strip is quickly rolled into a tight cylinder, mimicking the appearance of a small, rolled taco or taquito. This is done at high speed, often in under a second per piece, with careful calibration to prevent unrolling or uneven shapes. The rolling units must operate with precise timing and alignment, as even small inconsistencies could result in defective product or downstream clogging. Once formed, the raw Takis are transferred onto a mesh conveyor belt that carries them into the continuous fryer. Unlike air-puffed snacks, Takis achieve their final texture and flavor through frying in hot oil. The frying process occurs in large stainless steel fryers filled with high-stability vegetable oil, typically corn or sunflower oil. The oil is maintained at a consistent temperature, usually around 350 degrees Fahrenheit, and is constantly filtered and replenished to maintain quality and prevent flavor degradation. As the Takis pass through the fryer on a conveyor, they cook rapidly, the exterior crisping while moisture evaporates from the interior. This gives Takis their signature crunch, dense and satisfying, with just enough resistance to offer a unique mouthfeel. The fry time is carefully controlled, usually around 30 to 60 seconds, to ensure even cooking without burning or excessive oil absorption. Temperature sensors, oil flow meters, and automated timing systems monitor every batch, with defective products automatically rejected by vision systems downstream. As soon as they exit the fryer, the Takis must be cooled rapidly to halt cooking and prepare them for seasoning. The hot snacks are dropped onto a vibrating cooling conveyor, which uses forced, ambient, or chilled air to bring their temperature down quickly. This conveyor system not only cools, but also aligns and spreads the product evenly, preventing clumping before seasoning. And this is where the flavor magic happens. Takis are famous for their bold and intense seasoning blends, most notably the Fuego variety, which combines hot chili pepper and lime. The cooled snacks enter a large rotating tumbler or flavor drum, where they are coated with a fine mist of oil or flavor adhesive, such as maltodextrin or gum arabic. This light coating ensures the powdered seasoning sticks uniformly to the surface. Then, a precisely metered amount of dry seasoning blend is sprayed onto the rolling Takis within the drum. The tumbler rotates at a controlled speed, ensuring that every piece receives an even coating of the intensely red, flavor-packed powder. The powder itself is a carefully engineered blend of spices, acids, artificial flavors, and colorants, many of which are micro-encapsulated to preserve potency until consumption. This step is where flavor engineers shine, crafting bold profiles that hit the palate in waves. First, the citrusy tang of lime, then the slow-building burn of capsaicin from chili powder, followed by savory umami notes and salt. Once the Takis are evenly coated with their signature seasoning, the product advances to the post-seasoning inspection stage. Here, quality control takes center stage. As the finished snacks move down the conveyor belt, they pass through a combination of optical sorters, weight sensors, and human oversight stations. These systems are tasked with identifying any irregularities, broken pieces, improperly seasoned rolls, or foreign particles. High-speed cameras analyze each item against a programmed standard, with air jets used to automatically divert defective snacks from the production line. This meticulous approach ensures uniformity in every batch, both in appearance and taste. After clearing inspection, the freshly seasoned Takis enter the final phase of the production process: packaging. In large-scale manufacturing operations, packaging is not merely about enclosing the product in a bag. It's a tightly orchestrated, high-speed operation designed to maintain freshness, ensure food safety, and optimize shelf life. The cooled Takis are funneled into hoppers that portion them into individual servings. These hoppers are mounted above form-fill-seal machines, or FFS machines, which are the heart of the packaging operation. Each FFS unit starts with a continuous roll of multi-layered packaging film. This film is typically made from a combination of materials such as polyethylene, aluminum, and polypropylene. These layers provide essential barrier properties, keeping out oxygen, light, and moisture, elements that would otherwise degrade the snack's flavor and texture. The film roll is unwound, shaped into a tube, and sealed along its vertical edge using heat sealing bars. Simultaneously, the bottom of the tube is sealed to form a pouch, into which a precise dose of Takis is dropped from the hopper above. As the filled pouch moves through the machine, a horizontal seal is applied at the top, closing the package and completing the bag. The result is a perfectly sealed, shelf-ready snack pouch. Some facilities also inject an inert gas, typically nitrogen, into each bag before sealing. This process, called nitrogen flushing, displaces oxygen and helps prevent oxidation of the oil and spices inside the snack. It's a key technique in preserving freshness for weeks or even months after production. But the packaging line doesn't stop there. Once sealed, the Takis bags are conveyed to the labeling and coding station. Here, high-speed inkjet printers apply critical data to each bag, including production date, batch code, and expiration date. These codes are essential for traceability, enabling both the manufacturer and regulatory bodies to track products through the supply chain and, if necessary, initiate a recall. In larger factories, barcode scanners validate each print in real time, flagging any unreadable or incomplete prints for immediate rework. Next, the finished snack bags are grouped into larger quantities for secondary packaging. Robotic arms equipped with suction grippers or mechanical claws pick up batches of bags and place them into cardboard cartons or shrink-wrapped bundles. These secondary units are ideal for distribution to retailers, vending machine suppliers, and food service channels. Automated case erectors, packers, and palletizers handle this stage with minimal human intervention, ensuring consistency and speed. Once boxed, the cartons are scanned one final time, then transported to the warehouse using automated guided vehicles or conveyor systems. The warehouse itself is climate controlled, maintaining ideal conditions for snack storage, typically around 70 degrees Fahrenheit and low humidity. Inventory management systems track every pallet, integrating with enterprise resource planning software to coordinate distribution across multiple regions and customer channels. At this stage, Takis are officially ready for distribution. Depending on the destination, pallets may be routed to regional distribution centers, export facilities, or directly to major retailers. In the US, this typically involves refrigerated trucks or dry vans with temperature and humidity monitoring systems to ensure the product remains in peak condition throughout transport. For international shipments, Takis are loaded into containers and shipped via freight lines, with each load accompanied by customs documentation, certificates of analysis, and food safety verification records. It's important to note that all these stages, milling, extrusion, frying, seasoning, packaging, and shipping, operate under strict regulatory compliance and food safety protocols. The Takis manufacturing facility is typically audited regularly by health authorities and third-party certification bodies to maintain good manufacturing practices and adherence to standards such as the Global Food Safety Initiative. HACCP, or hazard analysis, and critical control points is implemented throughout the line to identify and mitigate risks, from biological contamination to mechanical hazards like metal fragments. Metal detectors and X-ray machines are also integrated into the production line post-frying and pre-packaging. These systems serve as a critical control point, scanning every product to detect foreign objects that could compromise consumer safety. In the rare event a contaminant is found, the system immediately shuts down the line and activates traceability protocols, ensuring the source of the contamination is quickly identified and corrected. In addition to food safety, automation plays a crucial role in the consistency and scalability of Takis production. Modern factories are outfitted with CAD systems, supervisory control, and data acquisition, which allow operators to monitor and adjust every part of the process in real time. Temperature readings, fry times, dough consistency, seasoning distribution, packaging integrity, all of it is visible from centralized control rooms staffed by trained technicians. These systems also gather historical data, enabling predictive maintenance and process optimization over time. Moreover, the human element remains vital. Quality assurance personnel regularly conduct sensory evaluations to ensure the finished product matches the flavor, aroma, and texture profile that consumers expect. Samples are pulled at set intervals and subjected to detailed analysis, including moisture content testing, oil content analysis, pH measurements, and microbial testing. These assessments help maintain product consistency and detect any early signs of spoilage or variation. And let's not forget the environmental impact. Many modern snack food factories, including those producing Takis, are actively investing in sustainable practices. Waste heat from fryers is often reclaimed and used to preheat water or air elsewhere in the facility. Oil used in frying is filtered and recycled several times before final disposal. Packaging materials are increasingly being sourced from recyclable or biodegradable films, and energy-efficient motors and lighting systems reduce overall factory emissions. The success of Takis also hinges on innovation. Flavor development is a continuous process involving food scientists, sensory analysts, and marketing teams. New flavors are often trialed in small-scale batch lines within pilot plants, where formulation tweaks can be made rapidly without disrupting full-scale production. Once a new variety passes consumer testing, it's scaled up to the main line, where production parameters are adjusted to accommodate the unique characteristics of the new seasoning blend. In essence, every bag of Takis represents a fusion of ancient techniques and cutting-edge food science. From the Mesoamerican tradition of nixtamalized corn to the robotic arms and AI-controlled inspection systems of a 21st century factory, the journey from cornfield to snack aisle is a marvel of industrial engineering. The attention to detail, the layers of safety checks, the complex choreography of machines, and human oversight all come together to create that iconic crunch and fiery kick that snack lovers around the world have come to crave. Once the freshly sealed Takis packages leave the manufacturing floor, their journey is far from over. The next phase, post-factory logistics and storage, is just as critical to the integrity of the final product. From the moment those pallets are loaded onto the loading docks, every step must be meticulously orchestrated to maintain freshness, comply with regulatory requirements, and meet retailer timelines. Palletized shipments of Takis are typically staged in designated outbound logistics zones within the factory's warehouse. Here, inventory management systems, integrated with warehouse management software, guide automated forklifts or human operators in sequencing outgoing loads. Each pallet is tagged with RFID or scannable barcodes, providing traceable data like batch number, production date, customer destination, and handling instructions. This is especially vital in high-volume operations where hundreds of thousands of units move through daily. Distribution of Takis often begins with transfer to regional distribution centers, or RDCs. These massive hubs serve as strategic points between the manufacturing facility and the retail shelf. Transportation is conducted via trucks equipped with climate control systems to protect the product from temperature spikes or humidity, both of which could compromise the texture and flavor of the highly seasoned snack. Although Takis are non-perishable, they are still sensitive to environmental conditions due to the oil content and delicate nature of their fried, rolled structure. Upon arrival at RDCs, the pallets are unloaded and sorted according to their final destination. Some may be earmarked for export, requiring additional customs documentation and compliance with international food labeling standards. For domestic markets, the focus shifts to inventory allocation, wherein Takis are divided among retailers based on demand forecasts, sales trends, and marketing campaigns. Algorithms calculate optimal shipping routes and timelines to minimize storage time and maximize shelf life for consumers. In-store delivery typically occurs on a just-in-time basis. Retailers prefer to receive snack shipments shortly before they are needed for shelf restocking to reduce their own warehousing costs. Specialized delivery trucks make daily or weekly runs to supermarkets, convenience stores, gas stations, and even vending machine distributors. Each of these retail environments poses unique packaging and merchandising challenges, all of which were anticipated back at the design and branding stage of the Takis production cycle. One of the unsung heroes in the journey of Takis is the shelf life optimization strategy. Although the product is fried, which naturally reduces moisture content and microbial activity, the seasoning powders and oils are susceptible to degradation over time. To combat this, manufacturers employ a suite of preservation techniques. Nitrogen flushing, as mentioned earlier, displaces oxygen in the sealed package, but antioxidants like tocopherols or rosemary extract are often blended into the seasoning to prevent rancidity. Additionally, desiccant sachets are sometimes included in bulk packaging layers to absorb ambient moisture during long-haul shipping. Once Takis make it to the retail environment, product rotation and visual appeal become the next critical concerns. Merchandising teams work with stores to position Takis in eye-catching locations, often near checkout counters or in custom display racks. Packaging design plays a crucial role here. The vivid purple of the Fuego flavor, for instance, has become iconic. This is not accidental. It is the result of extensive consumer psychology research and competitive shelf analysis. The packaging is printed using high-intensity inks and UV-cured varnishes that resist fading under fluorescent retail lighting. Meanwhile, behind the scenes, the manufacturer continues to monitor product performance through various feedback loops. Point-of-sale data is constantly reviewed to identify hot-selling regions, seasonal trends, and underperforming SKUs. Social media sentiment analysis and direct consumer feedback also guide adjustments in flavor intensity, packaging size, and promotional strategies. All of this feeds back into the product lifecycle management software, which helps guide future production and flavor development decisions. Speaking of flavors, one of the most fascinating aspects of the Takis operation is the flavor innovation pipeline. Flavor development is not merely a matter of combining spices. It's a complex interplay of sensory science, market forecasting, and precision engineering. Within dedicated R&D facilities, flavor scientists and food technologists explore new seasoning blends that push boundaries while remaining accessible to a wide audience. Using a combination of gas chromatography, mass spectrometry, and trained sensory panels, they deconstruct flavor experiences into measurable data points. For example, developing a new flavor like Dragon Sweet Chili or Blue Heat begins with identifying flavor trends in regional and global markets. Are consumers leaning toward Asian-inspired profiles? Are younger audiences seeking spicier, more adventurous options? Once a flavor theme is chosen, food scientists begin formulating dry seasoning blends that meet those goals. These blends are then micro-encapsulated to maintain potency through the frying process, ensuring that the end product retains its flavor intensity after months on the shelf. Prototypes are created on small-scale extrusion and seasoning lines within pilot plants. Here, the entire Takis production process is simulated at a reduced scale. This allows for rapid testing of texture, color retention, seasoning adhesion, and oil interaction without interrupting full-scale operations. Multiple iterations may be required before the formula is finalized. Once approved, the new flavor is scaled up and introduced into the market through limited releases or promotional campaigns. Based on consumer reception, it may join the permanent lineup or serve as a limited time offering. But with every new flavor comes new challenges. Seasoning powders vary in density, oil absorption, and electrostatic properties, all of which affect how they adhere to the snack. The tumbler rotation speed, spray nozzle angle, and even drum temperature may need to be recalibrated to accommodate different blends. For spicy varieties, capsaicin levels must be carefully controlled not only for flavor balance, but also to comply with regional regulatory thresholds for spice labeling. Some jurisdictions require heat warnings if the Scoville rating exceeds a certain level. Furthermore, regulatory compliance is a continuous effort in every phase of production. Labels must accurately reflect ingredients, nutritional values, and allergens. In countries like the US, compliance with FDA labeling laws is mandatory. In the European Union, Takis must also adhere to FSA food additive regulations and translation requirements. This means each regional variant may have slightly different formulations or packaging to meet local standards. Another area of innovation is sustainability. Snack food factories around the world are under increasing pressure to reduce their environmental footprint. The Takis production chain is no exception. Some facilities have introduced biodegradable packaging options for select markets, while others have invested in solar panels and high-efficiency fryers to cut energy use. Spent cooking oil is now commonly collected and converted into biodiesel, and water used in nixtamalization is filtered and reused for non-contact applications like equipment cooling. Sustainability also intersects with supply chain ethics. Corn suppliers are vetted not only for quality and price, but also for compliance with labor and environmental standards. Supplier audits are conducted regularly, and digital traceability platforms are used to map the corn's journey from field to fryer. This level of visibility allows the manufacturer to ensure that every ingredient in a Takis snack aligns with their corporate responsibility goals. Takis, for all their fiery boldness and snackable appeal, are a masterclass in food engineering and global logistics. They represent what happens when cultural flavors are married with advanced manufacturing, when age-old ingredients are given new life through extrusion science, and when every detail, from the grind of the corn to the curve of the roll, is tuned for maximum consumer satisfaction. As the Takis brand continues to evolve, the role of emerging technology in snack production becomes increasingly pronounced. Digital twins, for instance, are now being introduced in advanced food manufacturing environments. These are real-time digital replicas of the physical production line, complete with sensors, predictive analytics, and machine learning algorithms. By modeling the entire extrusion and frying process digitally, operators can simulate how small changes in variables, such as dough moisture content, oil temperature, or seasoning particle size, will impact the final product before making physical adjustments. This minimizes downtime, reduces waste, and enhances consistency across batches. Artificial intelligence and machine vision systems are also revolutionizing quality control. High-resolution cameras paired with deep learning algorithms can now detect subtle flaws that human inspectors might miss, such as uneven seasoning, microfractures in the rolled snack, or variations in color that could indicate improper frying. These systems learn over time, refining their detection capabilities with each batch they analyze. This not only improves product quality, but also enhances traceability and accountability within the plant. One particularly forward-looking development is in the realm of alternative ingredient sourcing. As demand for gluten-free, vegan, and allergen-free snacks continues to rise, food scientists are exploring reformulations of Takis that use alternative flours, such as chickpea, lentil, or sorghum flour. These flours come with their own extrusion challenges, especially when it comes to texture and structural integrity. Specialized extruder screws and preconditioning treatments may be necessary to match the crispness and density of the original corn-based recipe. Flavor delivery is another frontier being actively developed. Microencapsulation technologies are growing more sophisticated, allowing for flavors to be released sequentially as the snack is chewed. This creates a dynamic sensory experience, perhaps a burst of lime, followed by a wave of chili heat, then a subtle, lingering smokiness. These multi-layered flavor profiles are tested rigorously in consumer panels and sensory booths, with metrics like aftertaste duration, palate burn intensity, and residual coating all logged and analyzed. All these innovations are feeding into a broader trend: personalization. The concept of mass-customized snacks, where consumers can choose their preferred heat level, flavor intensity, or seasoning combo, may soon become viable thanks to modular production lines and just-in-time mixing systems. Imagine entering a vending machine interface or online store where you could build your own Takis variant, which is then mixed and packed to order within minutes. Toblerone chocolate production begins with the sourcing and intake of its core raw materials: cocoa mass, cocoa butter, sugar, milk powder, honey, almonds, and soy lecithin as an emulsifier. The distinct taste of Toblerone, known for its smooth Swiss milk chocolate interspersed with chewy nougat and honey almond notes, relies on both the precision of ingredient handling and the consistency of every preparation stage. The factory intake process starts with the arrival of these ingredients at the manufacturing plant's loading bay. Each ingredient is stored and transported under specific conditions tailored to its nature. For example, cocoa mass and cocoa butter, which are highly sensitive to temperature and oxidation, are delivered in thermally stabilized containers that keep them in a semi-solid state. Upon arrival, these containers are immediately transferred into insulated storage tanks inside the facility to prevent exposure to ambient air and humidity. These tanks are purged with inert nitrogen gas to minimize oxidation and preserve flavor integrity. Milk powder, sugar, and lecithin arrive in sealed food-grade sacks or large bulk bins and are lifted by pneumatic suction systems into silo units for temporary storage. Before anything enters the production stream, comprehensive quality assurance testing is conducted. Samples from each delivery are checked for microbiological safety, color, flavor, moisture content, and texture. Specialized equipment such as near-infrared spectrometers and rotary viscometers are used to assess these parameters in real time. Once verified, the production of the chocolate base begins. This base, which will serve as the core medium for all Toblerone bars, is created by combining cocoa mass, cocoa butter, sugar, and milk powder. Each of these components is dispensed into high-capacity stainless steel mixers in precise ratios dictated by the Toblerone formulation. These mixers are automated and fitted with load cells to ensure that each ingredient is weighed to the gram before being introduced to the blend. The contents are mixed at low speed to ensure a homogeneous distribution of particles without excessive aeration. This preliminary mixture, however, is far from the final silky chocolate. At this stage, the texture is coarse and grainy. To refine it, the mix is fed into a 5-roll refiner. The 5-roll refiner is a massive piece of machinery consisting of 5 horizontally aligned steel rollers that compress and shear the chocolate particles down to a size between 18 and 25 microns. This reduction in particle size is critical for mouthfeel. If particles remain larger than 30 microns, the human tongue perceives a gritty texture. Below 20 microns, the chocolate begins to melt smoothly and luxuriously in the mouth. During refining, sensors continuously monitor the gap between rollers and particle fineness using real-time laser diffraction analysis. Excessive refining can result in overheating or fat separation, so the temperature of each roller is actively cooled and monitored to maintain uniform conditions. The refined paste exits the refiner as a silky, thick, and slightly warm material, ready for the next stage, conching. Conching is the step where Toblerone's flavor is truly developed and its texture perfected. The conche machine is a large enclosed vessel that contains mechanical arms or rotors that knead the chocolate mass for several hours. This process serves multiple purposes. First, it evaporates unwanted volatile compounds, such as acetic acid or aldehydes, that may have formed during roasting or refining. Second, it distributes the cocoa butter evenly around each solid particle, coating them thoroughly and improving the overall flow behavior of the chocolate. The conching process typically lasts between 6 and 12 hours, depending on the batch size and the desired profile of the chocolate. During this time, emulsifiers such as soy lecithin are added to reduce the chocolate's viscosity without increasing the fat content. This makes the chocolate easier to mold and coat, while also enhancing its melt-in-the-mouth properties. It is also during conching that the iconic honey and nougat flavor notes of Toblerone begin to be layered in. Honey is added in measured amounts, not just for sweetness, but also to contribute to the product's distinct aroma and chewiness once combined with nougat. The factory conching process uses controlled heat, usually between 45 degrees Celsius and 80 degrees Celsius, to keep the cocoa butter in a liquid state. Temperature control is crucial. Too hot, and the chocolate risks burning or developing off flavors. Too cold, and the process slows, failing to drive off sufficient moisture. Modern conches are equipped with real-time pH, moisture, and volatile compound sensors that feed back into the control system, allowing operators to adjust mixing speed, arm pressure, or temperature on the fly. Once the conching is complete, the resulting chocolate is an ultra-smooth, shiny, and aromatic mixture. It is pumped into jacketed holding tanks that keep it at a stable temperature of around 30 to 32 degrees Celsius, ideal for downstream processes such as tempering and molding. These tanks are constantly agitated to prevent fat separation and crystallization. The next stage, tempering, is a pivotal process that controls the crystal structure of cocoa butter in the chocolate. Cocoa butter can crystallize in several different forms, but only one form, Form V, produces chocolate that is glossy, firm, and resistant to melting at room temperature. Achieving this form requires carefully heating and cooling the chocolate through a specific temperature curve. Tempering is done in continuous tempering machines where chocolate is first heated to around 45 degrees Celsius to eliminate all previous crystal formations, then cooled down to approximately 27 degrees Celsius to initiate the formation of stable seed crystals. The chocolate is then gently reheated to around 31 to 32 degrees Celsius to eliminate any unstable forms and maintain only the desired crystalline structure. These temperature transitions are tightly controlled by heat exchangers and thermal sensors, which ensure that the flow and crystallization kinetics of the chocolate are kept within narrow limits. With the tempered chocolate now perfectly conditioned and held at its ideal working temperature, it's time to move into one of the most distinctive and meticulously engineered steps of the entire Toblerone production process: molding the chocolate into its iconic triangular bar shape. This is not simply about pouring chocolate into a unique mold. It involves a detailed and highly synchronized series of movements designed to maintain structural integrity, precision alignment, and uniformity across millions of units. The Toblerone mold consists of a series of equidistant triangular cavities arranged in a straight line. Each mold cavity is designed to hold a single triangle of the bar, with narrow necks between them that allow for precise chocolate flow while ensuring each triangle remains individually defined yet conjoined. These molds are made of food-safe, high-strength polycarbonate and are preheated to prevent premature cooling when the liquid chocolate is deposited. Preheating ensures the chocolate flows evenly into every corner of the mold without setting too quickly, which could cause defects like air bubbles or incomplete shapes. Before chocolate enters the mold, the entire cavity array is vibrated at a high frequency using a precision-controlled shaker system. This vibration helps eliminate trapped air, allowing the chocolate to settle smoothly and evenly. The vibrating stage is calibrated to match the viscosity of the chocolate in real time, using inline sensors that monitor the chocolate's flow behavior. Any slight deviation in viscosity can affect how well the chocolate fills the narrow base points of the triangular molds, so the system adjusts shaker speed accordingly. Once the molds are filled, they pass under a leveling scraper to ensure the chocolate surface is perfectly flat along the bottom of the bar, which will ultimately become the base. A second, shorter vibration cycle occurs after this to further consolidate the chocolate and ensure all suspended particles, especially small bits of nougat or almonds, are evenly dispersed within each triangle. If the nougat or honey pieces were to settle unevenly during this stage, it would create inconsistent textures and affect quality. At this point, the filled molds are slowly moved into a multi-zone cooling tunnel. The tunnel is designed to gradually reduce the temperature of the chocolate from around 32 degrees Celsius to below 10 degrees Celsius over the course of several minutes. The zones begin with gentle ambient cooling, progressing through stages of increasingly chilled air, circulated by high-efficiency fans. The slow drop in temperature is crucial. If chocolate is cooled too rapidly, it can develop stress fractures, surface bloom, or uneven crystallization. The cooling system is monitored constantly using digital thermometers, hygrometers, and flow sensors to guarantee uniform airflow and humidity across every inch of the tunnel. As the molded bars pass through each zone, the cocoa butter crystallizes uniformly into the stable form V lattice structure, locking in glossiness and snap. This stage also causes the chocolate to shrink slightly away from the walls of the mold, which facilitates easy demolding later. Once the bars exit the cooling tunnel, they are still within the molds, but now fully solidified and dimensionally stable. Next, the demolding process begins. The molds are inverted onto conveyor belts equipped with soft silicone pads that cushion the fall of each bar as it's ejected. Demolding can be done either pneumatically, where jets of compressed air push the back of the mold to dislodge the bar, or mechanically, using plungers that gently press the chocolate out. In either case, sensors monitor the success rate of ejection, and any mold that fails to release the bar is automatically sent to a rework line. Once the Toblerone bars are released from the molds, they are briefly passed through an inspection station where machine vision systems check for mold, fill consistency, breakage, surface defects, and geometric conformity. High-resolution cameras and laser profiling tools compare each bar against stored 3D models. Bars that fall outside tolerance thresholds are marked for reprocessing, where they will be remelted and reintegrated into the production line. The successfully molded and cooled bars now enter the next phase, packaging. Before wrapping, each bar passes through a controlled dehumidification tunnel. This step is critical for preventing condensation during packaging, which could lead to microbial growth, sugar bloom, or spoilage. The dehumidifier maintains an environment below 30% relative humidity and gently warms the air around the chocolate to just above ambient temperature, allowing any moisture on the surface to evaporate without melting the chocolate. Once surface conditions are stabilized, the Toblerone bars move to the wrapping station. Here, the bars are individually picked and aligned onto a high-speed belt, where the characteristic triangular cardboard sleeve is automatically wrapped around each one. The sleeves are die-cut from pre-printed cardboard stock, folded precisely, and glued using food-safe adhesive. Each wrap is barcoded and batch-coded in real time, using inkjet printers synchronized with the production software. After the sleeve is applied, some product variations receive a foil wrapping beneath the cardboard. The foil is cut from gold-colored rolls and folded tightly around the chocolate by robotic arms using pre-programmed pressure patterns that ensure coverage without crushing the delicate points of the triangles. The foil serves as an oxygen and light barrier to prolong shelf life, especially for Toblerone products destined for warmer climates or long export journeys. Every wrapped bar is now scanned and weighed by automated inspection stations. Any unit that falls below or exceeds target weight, accounting for chocolate and packaging, is removed from the line for manual inspection. Those that pass all checks are sorted into bundles depending on product format: single bars, multi-packs, or gift sets. The bars are grouped into cartons by pick-and-place robots. These robots use suction cups and soft grippers to avoid damaging the points of the chocolate triangles. The cartons are then sealed, labeled with lot and traceability data, and stacked into master cases. Each master case is assigned a tracking code and loaded onto pallets using robotic palletizers programmed for maximum cube efficiency and stability. These pallets are then wrapped with stretch film and stored in temperature-controlled warehouses. Warehouse conditions are kept between 16 degrees Celsius and 18 degrees Celsius, with less than 50% humidity to prevent bloom and preserve texture. Pallets are logged into a central warehouse management system that coordinates batch rotation using FIFO principles, ensuring freshness upon delivery. Now that the Toblerone bars have been successfully molded, inspected, and packaged into their iconic triangular sleeves, the next stages of the factory operation transition from chocolate engineering into full-scale logistics, global adaptation, and product diversification, all of which require just as much planning, precision, and technical orchestration as the earlier phases of the chocolate creation itself. The journey from packaged bar to store shelf begins in the factory's outbound logistics area, where every finished pallet is scanned into the warehouse management system. The system integrates with enterprise resource planning software to track inventory levels, prioritize shipping based on destination climate, customs requirements, and expiration dates, and coordinate loading dock activity to maximize efficiency and avoid bottlenecks. At this point, temperature control becomes a dominant concern. Because chocolate is sensitive to thermal shock and prolonged exposure to high humidity or temperatures, all shipments are required to pass through insulated loading bays equipped with temperature buffering systems. These systems maintain consistent conditions even as trucks are loaded, preventing any temporary environmental spikes that might affect product integrity. For shipments destined for nearby distribution centers within a 200-kilometer radius, standard refrigerated trucks are used. These trucks are pre-cooled to the exact storage requirements, typically 16 to 18 degrees Celsius, and each one is fitted with temperature loggers and GPS tracking units that upload data to the central logistics server in real time. Any deviation in internal truck temperature during transit is flagged automatically, prompting quality control checks upon arrival. For export shipments, particularly to regions like Southeast Asia, Africa, or South America, Toblerone products are loaded into refrigerated shipping containers with independent power units, ensuring continuous cold chain conditions during ocean transport that may span up to 3 weeks. Each pallet is labeled with multiple identifiers, including product code, lot number, production time, line number, and temperature certification. These labels are printed using thermal transfer printers that embed RFID chips or scannable QR codes to allow full traceability. This level of detail is critical not only for internal logistics and recall management, but also to meet the regulatory requirements of import authorities in different countries. For instance, Gulf countries may require halal certification to be attached to the consignment, while Japan may demand documentation showing compliance with their unique food additive regulations. Toblerone's global logistics strategy is thus heavily embedded in regulatory compliance, with dedicated teams managing certification, customs documentation, and export logistics. Back within the facility, the production line doesn't operate in isolation. It's part of a broader, synchronized network of production scheduling. Toblerone is not produced as a single SKU, but in a wide variety of formats, each requiring slightly different processing configurations. These include the classic 100-gram bar, 50-gram snack bar, 360-gram gifting box, tiny 12.5-gram miniature pyramids, and specialty editions like white chocolate or dark chocolate variations. Each variation has a specific recipe profile, mold configuration, cooling requirement, and packaging format. Switching between variants requires a carefully managed process known as a changeover. A changeover begins with a complete emptying of all hoppers, pipelines, and depositors currently filled with one chocolate variant. The equipment is flushed using tempered cocoa butter or neutral chocolate mass to clear residual flavors and prevent cross-contamination. Then, the line undergoes a clean-in-place cycle involving detergent wash, water rinse, and final steam sanitization. Sensors measure residual proteins and fats in rinse water to confirm cleanliness. Only after quality control confirms a clean system does the new variant's ingredients enter the production stream. Changeovers also affect the molding system. For example, miniature Toblerone shapes are molded using smaller polycarbonate trays that are swapped in with robotic carriage systems. These molds pass through the same preheating, filling, vibration, and cooling steps as their larger counterparts, but on accelerated cycles due to their reduced volume and mass. The packaging system, too, must adapt. Larger bars require stronger folding cartons with inner trays, while minis are often flow-wrapped and placed into pouches or mixed assortment boxes. To handle this, the line includes modular packaging equipment that can be reprogrammed within minutes using preset SKU profiles. Operators scan a barcode for the new SKU, and all conveyor speeds, arm timing, and print data update automatically. A parallel stream of work takes place in Toblerone's research and development lab, often co-located with the factory or within the company's broader innovation campus. Here, food technologists and process engineers develop new flavor profiles, test alternative sweeteners, and design special edition runs tailored to holidays, partnerships, or regional taste preferences. For example, a limited edition bar infused with salted caramel may require different sugar crystallization controls, or a Ramadan edition might include date extract and modified packaging with Arabic text. Pilot-scale batches are created on miniaturized versions of the factory equipment, allowing experimentation without interrupting commercial-scale output. Every new recipe that graduates from R&D to factory production goes through a phase called scale-up validation. During this stage, the formulation is first made on a semi-commercial line capable of producing thousands of units per hour, and multiple parameters are tested: ingredient behavior under continuous agitation, flow characteristics during tempering, molding fidelity in standard production molds, and thermal stability during cooling. If the results meet the product development benchmarks, full-scale production is approved. Another important dimension of Toblerone's operation is environmental stewardship and factory sustainability. In recent years, the facility has upgraded many of its core systems to reduce carbon footprint, minimize waste, and improve energy efficiency. The chocolate tempering machines now utilize closed-loop thermal exchange systems that recycle cooling energy from one process to another. The air handling systems in the cooling tunnels and clean rooms have been upgraded to variable speed drives and high-efficiency particulate air filtration, significantly cutting energy usage while maintaining product safety. In terms of ingredient sustainability, Toblerone's cocoa is sourced under certified ethical sourcing programs. which ensure that the farms supplying cocoa beans are paid fairly, do not use child labor, and implement agroforestry practices that support biodiversity. These cocoa beans are processed into cocoa mass and cocoa butter by contract processors who follow Toblerone's strict quality and sustainability protocols, including traceability from farm to factory. The almonds and honey, too, are held to exacting standards. Almonds are supplied by certified orchards in California or the Mediterranean, sorted for size and oil content. Honey is sourced with attention to floral origin, ensuring a consistent flavor batch after batch. In-house testing includes pollen analysis, sugar spectrum fingerprinting, and moisture checks. This commitment to sourcing excellence reinforces the brand's identity as a premium Swiss chocolate. Finally, consumer safety and food compliance are at the core of every step of the Toblerone factory. All areas of the facility are subject to strict zoning protocols, separating raw ingredient handling from finished product areas to prevent contamination. Staff undergo regular hygiene training, wear full protective clothing, and enter through sanitation airlocks that include hand washing, boot scrubbing, and compressed air garment cleaning. Equipment is built to hygienic design standards, with no exposed threads, crevices, or moisture traps. Quality assurance checkpoints occur at dozens of locations throughout the line. Metal detectors are installed post-packaging to catch any foreign material. Check weighers ensure that each unit falls within exact mass tolerances. Barcode scanners verify packaging accuracy. And final batch records are signed off by a trained quality technician before any shipment is released. Even the slightest anomaly, an over-tempered batch, a slightly tilted mold, a misaligned wrapper, is caught, logged, and addressed through a root cause analysis process. Every detail matters because Toblerone is not simply a chocolate bar. It's a global symbol of quality, tradition, and precision engineering. What looks like a single, satisfying triangle is actually the result of hundreds of synchronized decisions, operations, and technologies that function in harmony to deliver an unchanging standard of excellence. With the full-scale production, molding, packaging, and international logistics already finely tuned, the final stages of Toblerone's manufacturing process revolve around final distribution, continuous improvement protocols, consumer-facing customization, and digital integration that modernizes how quality and efficiency are sustained across an ever-growing global demand. Once pallets of finished, labeled, and verified Toblerone products are ready for shipment, they enter the outbound logistics management system, where real-time data on shipping routes, order queues, and warehouse availability determine where each batch goes next. The system doesn't just track inventory, it optimizes routes based on transportation cost, shelf life preservation, retail replenishment cycles, and sales forecasts provided by global distribution partners. Whether a shipment is bound for a Swiss airport duty-free zone, a North American grocery chain, or an e-commerce fulfillment center, its path is selected based on minimizing transit time and maintaining perfect storage conditions. Each truck or container that leaves the factory is accompanied by digital and printed documentation that includes compliance declarations, temperature logs, ingredient traceability records, and destination-specific export certificates. These are often required at borders for customs clearance, particularly in markets with strict regulations around food labeling, allergens, or religious dietary requirements like halal or kosher certifications. The factory's compliance team works in sync with shipping personnel, constantly updating their records as international regulations evolve. Inside the production facility itself, continuous improvement is embedded at every level. Daily performance metrics are posted on digital displays throughout the production floor, tracking everything from machine uptime and output per hour to defect rates, waste percentages, and energy usage. Operators have access to touch panel controls that allow them to report faults or initiate adjustments on the fly. When an anomaly is detected, it's logged in a root cause tracking system that prompts follow-up from engineering or quality assurance teams. This immediate feedback loop is designed to prevent small issues from becoming systemic problems. Preventive maintenance also plays a major role in sustaining Toblerone's high production standards. Every piece of equipment in the line, from chocolate mixers to automated packers, is tagged with a maintenance schedule integrated into the plant's CMMS. Operators are prompted automatically when a belt needs replacement, a blade needs sharpening, or a motor requires lubrication. By minimizing unplanned downtime, the factory ensures consistency in output and avoids any deviation from scheduled production volumes. Consumer customization is another frontier in Toblerone's manufacturing strategy. For promotional seasons, corporate gifting campaigns, or regional celebrations, Toblerone offers limited edition bars with printed names, holiday messages, or even national flag motifs. The core of Coca-Cola's production begins at the local bottling facility. These factories are strategically located around the world to minimize transportation time and maximize freshness. While the Coca-Cola company maintains control over the flavor concentrate, the bottling partners are responsible for the bulk of production, mixing, bottling, packaging, and distribution. But before anything is mixed, the most vital ingredient must be treated first: water. Water makes up over 85% of Coca-Cola, and its quality directly affects the flavor, clarity, and shelf life of the product. Municipal water is drawn into the plant and subjected to an advanced, multi-stage purification process. It begins with coarse filtration to remove sediment and particulates. From there, the water passes through activated carbon beds, where chlorine and organic compounds are stripped out. Next comes reverse osmosis, or ultrafiltration membranes, which remove dissolved salts, metals, and microorganisms. This purified water then undergoes ultraviolet light treatment, or ozonation, to ensure biological sterility. The goal is to achieve ultra-pure, neutral-tasting water that provides a blank canvas for the Coca-Cola flavor. Constant inline sensors monitor for pH, turbidity, and conductivity, ensuring every liter meets exacting standards before it ever touches the syrup. Next, the flavor base is prepared. The concentrated Coca-Cola syrup arrives at the factory in sealed, food-grade containers. Its precise formulation remains a closely guarded secret, known internally as Merchandise 7X. What we do know is that the concentrate contains sweeteners, acids, caramel coloring, caffeine, natural flavors, and essential oils derived from citrus peels and spices. This concentrate is mixed on-site with additional ingredients, often in a syrup blending station, to create a finished syrup. The syrup blending process is conducted in stainless steel tanks equipped with high-shear mixers and recirculation pumps. These ensure the thick concentrate is uniformly mixed with water, sweeteners, and phosphoric acid, one of the key flavor-defining agents. In most regions, high fructose corn syrup is used as the sweetener, though in others, such as Mexico and parts of Europe, cane sugar is used instead. The blending tanks are temperature controlled and sealed to avoid contamination, and every batch is sampled and lab tested before moving forward. With the syrup mixed and the water purified, the next step is combining the two. This happens in a piece of equipment known as a proportioner. Here, the syrup and treated water are blended at precise ratios, usually around 1 part syrup to 5 parts water, under tight quality control. The proportioner ensures the mix is homogeneous and delivers the same flavor intensity in every can or bottle, no matter where it's made in the world. Now comes the science of carbonation. Carbon dioxide gas, stored in large pressurized tanks on site, is injected into the finished beverage mixture using a carbonator. The carbonator chills the liquid to just above freezing, typically around 33 to 38 degrees F, because cold water can hold more dissolved gas. The beverage passes through a sintered stainless steel sparger or fine bubble diffuser, which allows the CO2 to saturate the liquid evenly. This gives Coca-Cola its signature effervescence, a process carefully controlled to maintain consistent volumes of CO2, typically between 2.5 and 3.0 volumes. At this stage, the finished product, cold, carbonated Coca-Cola, is transferred to an insulated holding tank under gentle pressure. From here, it is ready to be packaged. And this is where the production line truly comes to life. In a modern bottling plant, packaging lines run at astonishing speeds, filling and capping up to 1,200 bottles per minute or more. But before any beverage enters a container, the containers themselves, whether glass bottles, plastic PET bottles, or aluminum cans, must be cleaned and prepared. PET bottles arrive pre-formed and are blown into full-size bottles on-site using a stretch blow molding machine. This reduces transport volume and increases efficiency. Once formed, each bottle is rinsed or sterilized using ozonated water or clean steam. This eliminates microbial contamination and dust particles. Cans and glass bottles undergo similar sterilization processes, often involving high-pressure air jets or a tunnel washer that uses multiple rinsing stages. Clean containers then move into the filling carousel. This is a high-precision rotary filling machine with dozens of synchronized nozzles, each calibrated to deliver exactly the right volume of Coca-Cola into each bottle or can. The filling occurs under pressure to prevent foaming and loss of carbonation. A vacuum seal may be briefly applied to ensure the gas stays dissolved in the liquid. Immediately after filling, the containers move along the carousel to the capping or sealing station. For PET bottles, tamper-evident screw caps are applied using torque-controlled capping heads. For cans, an aluminum lid is crimped on using a seamer. Glass bottles receive a crown cap applied with pneumatic presses. These closures are crucial not only for sealing in freshness, but also for maintaining carbonation levels throughout the product's shelf life. Once sealed, containers move rapidly to the date coding and inspection stations. Here, inkjet printers mark each unit with its production time, lot number, and best before date. Simultaneously, high-speed cameras and check weighers verify fill levels, cap integrity, label alignment, and overall container quality. Any anomaly triggers a pneumatic arm to remove the item from the line instantly. Bottles and cans are then grouped and packed for shipping. Smaller units may be shrink-wrapped into 6-packs or inserted into cardboard carriers. Larger cases are assembled by robotic arms into corrugated boxes or pallet layers. Palletizers stack the boxes into tall, stable configurations and apply barcoded stretch wrap for secure transport. At this point, Coca-Cola is nearly ready to leave the facility, but not before one last layer of control. Samples from every batch are retained and sent to the quality assurance lab, where a battery of tests is performed. These include sensory evaluations by trained tasters, gas volume testing with CO2 analyzers, Brix level measurement to confirm sweetness, and acid titration for pH control. Only after passing all these checkpoints is the batch released for distribution. The finished product is stored in a climate-controlled warehouse, maintained at ideal conditions to prevent spoilage or bottle expansion. From here, the Coca-Cola is dispatched via refrigerated trucks or temperature-monitored dry vans. Logistics teams coordinate shipments to supermarkets, restaurants, vending distributors, and retail centers using inventory tracking systems that ensure first-in, first-out rotation and traceability in case of recalls. Behind the scenes, the entire system is monitored by a sophisticated SCADA platform that links water purification, blending, carbonation, and packaging into a unified, real-time control interface. Operators can adjust flow rates, tank temperatures, carbonation pressure, and even cap torque from centralized dashboards. Predictive maintenance alerts notify technicians when pumps, motors, or valves deviate from baseline performance, minimizing downtime. The scale is immense. A single Coca-Cola bottling facility can produce several million units per day across various formats, ranging from 8 Oz cans to 2-liter bottles, each undergoing its own production and packaging parameters. Automation is essential, but so is human oversight. Technicians, engineers, microbiologists, and logistics experts all play vital roles in ensuring every sip of Coca-Cola tastes exactly as it should, whether it's opened in Atlanta, Tokyo, or Cape Town. And yet, for all its complexity, the experience of drinking Coca-Cola remains simple: effervescent, sweet, slightly acidic, and unmistakably iconic. Each bottle is a product not just of secret formulas and clever marketing, but of some of the most advanced food manufacturing systems on Earth. From water chemistry to high-speed robotics, from syrup tanks to palletized crates, Coca-Cola's journey from factory to fridge is a meticulously choreographed process, engineered for both speed and perfection. To begin understanding how Dr. Pepper is made, we have to step inside one of the massive regional bottling facilities operated by licensed partners. These plants are the heartbeat of the Dr. Pepper supply chain. They don't just bottle soda, they engineer precision, maintain sterility, and manage staggering volumes of ingredients with scientific exactness. Everything begins with water. Although soda is often celebrated for its flavor, more than 85% of the final product is purified water. And not just any water, ultra clean, neutral, flavorless water that forms the foundation of every bottle. This means municipal or groundwater entering the plant must undergo intensive treatment. The first stage of this treatment process uses coarse filtration to remove large particles and suspended solids. Then, the water is passed through activated carbon beds to eliminate chlorine, chloramines, and any volatile organic compounds that could distort the flavor. From there, the process shifts to more advanced techniques. Reverse osmosis membranes, or ultrafiltration units, strip the water of minerals, microbes, and trace contaminants. Ultraviolet light, or ozonation, finishes the process, sterilizing the water and rendering it free of any taste or odor. The water is now ready, perfectly clean, chemically stable, and ready to receive the flavors that define Dr. Pepper. Parallel to this, syrup preparation takes place in a separate, sanitized mixing room. The base flavoring for Dr. Pepper arrives at the plant in concentrated form, pre-blended by the brand's flavor division under tight secrecy. These concentrates are stored in stainless steel containers and handled with care, with operators measuring and metering the required amounts into large batching tanks. In these tanks, often fitted with high shear mixers, agitation paddles, and precision load cells, the base concentrate is combined with purified water, sweeteners, and acids. Depending on the region, the sweetener may be high fructose corn syrup or cane sugar. The acid, usually phosphoric or citric, helps balance the syrup's pH and sharpness. The mixture is stirred and recirculated until it becomes a uniform, homogeneous syrup with exact Brix values, the measure of dissolved solids in a liquid, often used to calibrate sweetness levels. Before it moves forward, the syrup batch undergoes quality assurance checks. Technicians take samples and run tests in on-site labs, analyzing Brix, pH, color, and aroma. Only after it passes these strict controls is the syrup cleared for the next phase, beverage blending. In a process called proportioning, the syrup is metered and blended with purified water in exact ratios, typically around 1 part syrup to 5 parts water. This mixture becomes the flat, uncarbonated Dr. Pepper base. The proportioning system is controlled by flow meters and programmable logic controllers, ensuring that the mix is stable within a tight tolerance band. Every shift, every batch, whether it's in Texas, Ontario, or the Philippines, must deliver the same flavor profile. With the beverage mixed, it's time to add the fizz. carbonation is one of the most technically critical steps in soda production. The pre-mix Dr. Pepper is chilled to just above freezing, typically around 35 degrees, to increase its ability to absorb carbon dioxide. CO2 is stored in large tanks on site and is food grade, filtered, and monitored for purity. The cold liquid is forced through a carbonator where fine CO2 bubbles are injected under high pressure through porous diffusers or sintered steel plates. Proper carbonation is both science and art. If done poorly, the soda may foam excessively during bottling or taste flat when opened. The target for Dr. Pepper is usually around 2.5 to 3.0 volumes of CO2, enough to give it its characteristic zing without overwhelming the complexity of its 23 flavor blend. The carbonated product is now pressurized and ready for immediate bottling to prevent CO2 loss. The bottling line is where everything shifts into high speed. Depending on the plant, the line can handle glass bottles, aluminum cans, or PET plastic bottles. Most modern facilities use stretch blow molding machines to convert PET preforms into full-sized bottles on site. This reduces shipping costs and allows for rapid size changes depending on demand. Each bottle or can first passes through a rinsing or sterilizing system. Bottles may be inverted and blasted with ionized air or washed with ozonated water. Cans are typically rinsed with sterilized water before entering the filler. Now, the carbonated Dr. Pepper is dispensed into containers using a rotary filling machine. This machine features multiple filling heads rotating on a carousel, with each head delivering the precise amount of liquid into each container. The filler operates under pressure to prevent foam and retain carbonation. As soon as the beverage is deposited, the bottle or can is sealed. PET bottles are capped using torque-controlled screw heads, while cans receive crimped-on aluminum lids in a high-speed seamer. Immediately after sealing, the containers pass under printers that apply batch codes, production dates, and expiration information. This coding is essential for traceability. If there's ever a recall or quality issue, the plant can trace every bottle back to the exact minute it was produced, the syrup batch used, and the operator on duty. Then comes packaging. Filled bottles are grouped into packs using shrink film, cardboard sleeves, or trays, depending on the final retail format. These packs are stacked by robotic arms onto pallets in precise configurations optimized for transport. The finished pallets are stretch wrapped, labeled with shipment data, and moved to the distribution warehouse. But before any pallet is cleared for shipment, the line's quality control team pulls samples from each production run. These are subjected to rigorous testing in the plant's on-site laboratory. Pressure tests confirm carbonation levels. Spectrophotometers check color uniformity. Sensory experts conduct taste evaluations to verify the blend is balanced. Microbial samples are incubated to ensure the product is sterile and safe. Meanwhile, automation software monitors the entire plant. From SCADA systems that track syrup bricks and carbonation pressures to IoT-enabled sensors that measure temperature drift in holding tanks, the entire operation is visible in real time to engineers and technicians. If a motor starts to overheat or a fill level goes out of spec, alerts are triggered immediately. Once quality is assured, the finished product is ready for shipping. Climate-controlled logistics routes transport Dr. Pepper to warehouses, distributors, and retail outlets. Some trucks are refrigerated, especially in hotter regions, to protect the product during transit. Whether it's a vending machine in a high school, a 12-pack in a grocery store, or a fountain soda in a fast food chain, each container of Dr. Pepper must taste exactly the same. And that's only possible because every variable was controlled from start to finish. Beyond the factory, the Dr. Pepper production network also includes specialty manufacturing for fountain syrups, bag-in-box formats for restaurants, and concentrate shipments for international bottlers. These formats go through similar blending, filtration, and quality assurance processes, but are tailored for bulk use with different bricks and carbonation considerations. Every day, this system repeats across dozens of plants, with millions of cans and bottles produced and shipped with extraordinary consistency. Despite being made at different locations by different teams, every unit of Dr. Pepper shares the same flavor fingerprint: sweet, spicy, slightly fruity, with a creamy undertone and a signature bite. It's a beverage born in the 1880s, but produced today using some of the most advanced technologies in food manufacturing. From its mysterious blend of flavors to its perfectly balanced carbonation, Dr. Pepper represents a legacy of innovation, precision, and a dedication to quality that extends from syrup tank to store shelf. Sprite's story begins with water. While most people focus on Sprite's citrus flavor, the truth is that over 85% of what you're drinking is water. But not just any water. For Sprite to taste exactly the same in Singapore as it does in San Diego, bottling plants must purify their local water supply to a consistently neutral baseline, free from taste, color, odor, and minerals. The incoming municipal or well water is first screened through mechanical filters to remove suspended solids. It then moves through activated carbon filters that strip out chlorine, chloramines, and any volatile organic compounds. This ensures that the water has no off-putting flavors. Then it passes through either reverse osmosis membranes or demineralization columns, which remove dissolved salts and ions. Finally, a UV treatment or ozone injection kills any microorganisms. This ultra-purified water is held in stainless steel tanks, where it is monitored in real time for pH, conductivity, turbidity, and microbial counts. It must meet the exact specifications set by the Coca-Cola company before being allowed into any part of Sprite production. Only once it's passed all quality checkpoints can it be used to create the base for one of the world's most recognizable sodas. Parallel to the water treatment is the preparation of Sprite's proprietary flavor syrup. This part of the process is handled in a syrup blending room, often kept under positive air pressure and high sanitation standards to prevent contamination. The base concentrate used for Sprite, supplied by the Coca-Cola company, is delivered to the plant in sealed, food-safe drums or totes. This concentrate contains the citrus flavoring system, acidulants, and trace aromatic compounds that define Sprite's lemon-lime taste. Inside the blending tanks, equipped with high-torque agitators and recirculation loops, the concentrate is mixed with water and sweeteners to form the final syrup. The sweetener is usually high-fructose corn syrup in the United States, though in some countries, cane sugar is used instead. Citric acid and natural flavors help create that sharp, clean taste. The syrup is blended at specific Brix levels, a measure of sugar concentration, and is analyzed for consistency in labs adjacent to the blending floor. Once the Sprite syrup is blended and passes quality checks for color, taste, pH, and sugar content, it is sent to the proportioning system. This is where the final product begins to take shape. Inside stainless steel pipelines, the syrup is carefully metered and mixed with the purified water in precise ratios, generally around 1 part syrup to 5 parts water. This mixture is now the uncarbonated version of Sprite, flat, sweet, and citrusy, but still missing that all-important sparkle. Carbonation is added in the next step. The flat beverage mixture is chilled to near freezing, typically 33 to 36 degrees F, inside jacketed holding tanks. This is essential because cold water absorbs carbon dioxide much more effectively. A carbonator, one of the most critical pieces of equipment in the line, injects high-purity, food-grade CO2 into the chilled mix. The carbonation process is highly controlled. Bubble size, saturation level, and gas purity are all continuously monitored. Sprite generally carries between 2.7 to 3.0 volumes of CO2, giving it that signature effervescence and a sharp bite that enhances the citrus flavor. Once carbonated, the finished Sprite beverage is held under pressure in chilled, oxygen-free holding tanks. It is now ready for bottling, and this is where the production line hits its highest speed. The bottling line is a marvel of automation, capable of processing over 1,000 bottles or cans per minute, all synchronized to fill, cap, label, and inspect each unit with zero tolerance for error. First, the containers must be prepared. If PET bottles are used, they arrive as pre-forms, small, test tube-shaped blanks. These pre-forms are heated and stretch-blown into full-size bottles using high-pressure air inside precision molds. This process allows plants to manufacture bottles on-site, reducing shipping costs and allowing for quick changes in size or shape depending on market needs. The newly formed or delivered containers are then sent through a rinsing or sterilizing station. Bottles may be sprayed with ionized air, steam, or ozonated water to remove dust and kill microbes. Cans are similarly rinsed and then inverted before filling. The carbonated Sprite is then filled into each container using a rotary filling machine. The beverage must be filled under counter pressure to preserve carbonation and prevent foaming. Each filling nozzle is calibrated to deliver an exact volume, down to fractions of a milliliter. As soon as a bottle is filled, it immediately passes to the capping station. Caps and lids are fed in from hoppers and applied with high-speed capping heads that torque each PET bottle to specification. Aluminum cans are sealed with a crimping mechanism called a seamer, which attaches the lid using multiple rollers in rapid succession. The entire filling and capping sequence is enclosed within a clean, sterile zone to prevent contamination. With the product sealed, it's time for coding and inspection. Each unit is printed with a production code, batch number, and best before date using a high-speed inkjet or laser printer. Advanced camera systems immediately scan the bottles or cans for fill level, cap alignment, label position, and structural defects. Anything that doesn't meet specs is ejected from the line automatically. Now the finished bottles or cans are routed to the packaging area. Depending on the destination, they may be shrink-wrapped in multi-packs, inserted into cardboard carriers, or loaded into trays for larger retail formats. Robotic palletizers pick up these packs and stack them in precise layers, forming stable shipping units. Each pallet is stretch-wrapped, labeled with destination and production information, and scanned into the warehouse inventory system. Before these pallets leave the facility, the Sprite they contain has already been sampled for in-depth quality checks. Laboratory technicians pull random samples throughout each production run and test for bricks, pH, CO2 volumes, and sensory characteristics such as aroma, clarity, and taste consistency. These tests are performed hourly, sometimes more frequently, using calibrated instruments and trained panels. Additional microbiological testing ensures the beverage is free of spoilage organisms. Each batch must pass these hurdles before it is released for distribution. Some plants hold back every 10th or 20th pallet for additional hold and release protocols, where the beverage is stored under controlled conditions and monitored for early spoilage signs before shipment. From here, Sprite enters the logistics phase. Temperature-sensitive loading docks ensure that the product stays cool, especially in hot climates where carbonated beverages can suffer from premature expansion or loss of pressure. Climate-controlled trucks or standard dry vans, depending on the geography, transport the soda to distribution centers, retail warehouses, and vending machine operators. Behind the scenes, the entire operation is driven by powerful software, SCADA systems, programmable logic controllers, and cloud-connected ERP platforms. These monitor tank levels, syrup usage, CO2 flow rates, batch records, and even maintenance needs. Some lines are equipped with predictive analytics, using data to forecast failures before they occur, reducing downtime and ensuring maximum uptime. Every bottle and can of Sprite must conform to the same flavor fingerprint: balanced sweetness, bright citrus notes, clean finish, and a bracing level of fizz. Even with local water, different sweeteners, and various bottling partners worldwide, Coca-Cola's stringent standardization process ensures that no matter where you are, every Sprite you open tastes like it came from the same source. And yet, as science-driven as it is, the drink remains simple in experience. No caffeine, no color, just a bold, clear, citrus-flavored soda that delivers a refreshing hit with every gulp. A product of incredible precision, born in stainless steel tanks, shaped by sensors, robotics, and human craftsmanship, and enjoyed, often without a second thought, by millions. In the end, Sprite may be light and fizzy, but its production is anything but. It's the result of decades of process optimization, global logistics, sensory chemistry, and industrial control. And behind that cool green label lies one of the most tightly controlled and fascinating beverage production systems in the world. A crisp snap, a creamy melt, and a perfect balance of chocolate and wafer. KitKat is more than a candy bar. It's a confectionery icon, loved worldwide and instantly recognizable for its 4 slender fingers and clever tagline. KitKat stands as a shining example of how precision engineering, food chemistry, and high-speed automation can come together to craft something remarkably simple and yet technically intricate. To understand how KitKat is made in a factory, we have to start with its dual nature: half chocolate, half wafer. Each must be manufactured independently with extreme care, then combined at the right moment to create a product that tastes the same, whether it's made in Japan, the UK, or Canada. The process begins with the preparation of raw ingredients, and the base of it all is wheat flour, used for the crispy wafers. This flour is stored in towering silos, aerated and filtered to remove dust and contaminants. It's pneumatically conveyed to the mixing room, where it's combined with sugar, palm or sunflower oil, milk powder, salt, baking powder, and water. These ingredients are deposited into large, jacketed horizontal mixers, which knead them into a consistent, homogeneous dough. At this stage, automation systems monitor dough temperature and hydration levels, adjusting mixer speed and timing accordingly. Once the dough is ready, it's extruded into thin sheets. This happens on massive wafer sheet lines, flat conveyor belts, where rollers press the dough into sheets less than 2 millimeters thick. These sheets move through high-capacity baking ovens that use convection heat to evenly cook them. These ovens stretch over 50 feet long, operating at temperatures around 180-200 degrees. Each wafer sheet bakes for less than 2 minutes, but emerges dry, crisp, and golden, ready for layering. Now comes one of the most signature features of the KitKat, the layered wafer structure. Each wafer sheet is passed through a slathering station, where a precise amount of wafer cream, a chocolatey, fat-based paste, is applied to its surface. This cream, made from finely ground sugar, fats, milk solids, and cocoa powder, serves as both flavor and adhesive. Multiple layers of wafers and cream are stacked, typically 3 wafers and 2 cream layers, forming a block known internally as a wafer book. These wafer books are pressed under light pressure and sent through cooling tunnels to stabilize the cream. Once firm, they are sliced into individual fingers using ultra-sharp guillotine blades or water jet cutters. Each finger is a perfect rectangle, dimensionally identical to ensure they fit precisely into the chocolate molds in the next stage. Meanwhile, chocolate production is running in parallel. KitKat uses milk chocolate, which must be refined and tempered to perfection. The chocolate begins with cocoa liquor, cocoa butter, milk powder, and sugar, all blended together in mixing tanks. From there, the mixture is passed through refiners, a series of large rollers that crush and flatten the mixture into particles smaller than 20 microns. This size is critical to achieving the smooth mouthfeel expected of high-quality chocolate. After refining, the mix enters conching machines, giant heated vats where the chocolate is stirred, aerated, and aged for several hours. This removes bitter volatiles, improves texture, and develops flavor. Once conching is complete, the chocolate is tempered, a precise process of heating, cooling, and reheating the chocolate to promote the formation of stable cocoa butter crystals. Without this step, the chocolate would be dull, soft, or prone to blooming. Tempered chocolate has a shiny finish, satisfying snap, and melt-in-your-mouth consistency. Now the chocolate and wafer fingers are ready to unite. This happens on a molding line. First, plastic or stainless steel molds are warmed slightly and filled with a thin layer of tempered chocolate. This bottom layer forms the base of the KitKat. Then, the pre-cut wafer fingers are robotically placed onto the chocolate-filled molds. Another dose of chocolate is deposited over the top, fully enrobing the wafer fingers and completing the bar structure. The filled molds pass through a vibration table to remove air bubbles and ensure complete coverage. From there, they travel through a cooling tunnel, a refrigerated chamber where the chocolate crystallizes and solidifies. By the time the molds exit, the KitKat bars are fully formed, firm, and ready to be demolded. Demolding is fully automated. Each mold is flipped, and a gentle mechanical tap releases the bars onto conveyor belts. The now empty molds are cleaned, sterilized, and recirculated back into the system. The KitKat bars now move to quality inspection. Vision systems equipped with high-speed cameras scan every bar for size accuracy, surface defects, cracks, or incomplete coatings. If anything is off-spec, that bar is removed from the line. Approved bars continue on toward the flow wrapping station. Packaging is a crucial part of the KitKat experience, not just for branding, but also for shelf life. Each bar is wrapped in metallized plastic film that acts as a barrier to light, oxygen, and moisture. The flow wrappers operate continuously. Bars are fed onto belts, aligned by guide rails, and pushed through a forming collar where the film is wrapped around them and sealed with heat-sealing jaws. Wrapped bars are then grouped into multi-packs or secondary trays, depending on customer requirements. Robotic arms or pick-and-place machines assemble the bars into display-ready formats. These units are then placed onto pallets using automated palletizers and stretch-wrapped for transport. Every step of this process is monitored by SCADA systems and connected sensors. Mixing temperatures, dough moisture, oven humidity, chocolate viscosity, flow speeds, and packaging integrity are all logged in real time. If a parameter drifts outside the set range, alerts are triggered and corrective action is taken immediately, either by automatic control or operator intervention. Meanwhile, samples from every production lot are pulled and sent to the on-site quality assurance lab. Here, technicians run texture analysis, moisture content testing, shelf stability trials, and most importantly, sensory evaluations. Trained tasters assess whether the product matches the official profile: crisp but not dry, sweet but not cloying, and a melt that delivers the cocoa hit right before the wafer crunch. Beyond quality, KitKat factories are also designed with hygiene and allergen safety in mind. Separate lines may be maintained for peanut-free or gluten-free variations, and full allergen switchover protocols are implemented if recipes change. Stainless steel surfaces, clean-in-place systems, air filtration, and pressure-zoned rooms ensure that each environment is sanitary and safe. Sustainability is also an emerging pillar of KitKat's production. Many factories now source Rainforest Alliance certified cocoa, and water and energy recovery systems are implemented to reduce waste. Chocolate scraps and wafer trim are collected and reprocessed, either reused in internal production or recycled into other food streams. From raw wheat and cocoa beans to precision molded chocolate fingers, the production of KitKat is a dance of science and craftsmanship. It's easy to take for granted, something you grab at the store, tear open, and snap into without a second thought. But behind every bar is an extraordinary feat of coordination, timing, and innovation. It's the result of countless variables, all controlled within narrow limits, to ensure that when you have a break, you're rewarded with the exact flavor, texture, and snap you expect. Golden foil, delicate layers, creamy filling, and a whole hazelnut at the core. Ferrero Rocher is the epitome of premium chocolate craftsmanship. But what seems like a luxurious, handcrafted treat is actually the result of one of the most precise and sophisticated chocolate manufacturing operations in the world. Produced by the Italian confectionery giant Ferrero Group, Ferrero Rocher is a marvel of layered architecture and synchronized automation. And to truly understand how it's made, we must step inside the walls of one of their advanced, high-security confectionery plants. It all begins with the hazelnut, Ferrero's signature ingredient. The company is one of the largest consumers of hazelnuts globally and maintains close relationships with farmers across Turkey, Italy, and Chile. Only whole, uniform, high-grade hazelnuts are accepted for use in Ferrero Rocher. Upon arrival at the processing facility, the hazelnuts are cleaned to remove debris, shelled, and subjected to multiple rounds of size grading and visual inspection, both by machine and by human eyes. The hazelnuts are then gently roasted in continuous drum roasters. These large, rotating cylinders apply indirect heat to evenly roast the nuts without scorching them. Temperature and time are tightly controlled, typically around 150-160 degrees Celsius for 15 to 20 minutes. The goal is to enhance the nut's natural oils and flavor without damaging the internal structure. Once roasted, the nuts are cooled rapidly to halt the cooking process, then transferred to storage under nitrogen to preserve freshness. With the hazelnuts ready, attention turns to the wafer shell, the crisp, spherical layer that surrounds each nut. The wafer is made from a batter of wheat flour, water, sugar, oil, and leavening agents. The batter is deposited onto heated hemispherical molds in automated wafer baking machines. These molds close like clamshells, sealing and cooking the wafer until it forms a hollow, thin sphere. This process takes only seconds, and each wafer shell is then cooled, trimmed, and conveyed to the filling station. Now we move to the cream filling. This smooth, chocolate hazelnut cream is made using a proprietary blend of ingredients: cocoa, milk powder, sugar, and hazelnut paste. The hazelnut paste is prepared by finely grinding roasted hazelnuts into a silky nut butter, then blending it with cocoa solids, vegetable oils, and emulsifiers. The mixture is heated, homogenized, and passed through conching units to develop a smooth texture and balanced flavor. At this point, multiple streams converge. A whole roasted hazelnut is placed in the center of each wafer hemisphere. Then, a precise amount of the chocolate hazelnut cream is deposited into the cavity, encasing the nut. The wafer sphere is closed by joining two halves together with a light pressure and a ring of filling acting as an adhesive. Each filled wafer is now a complete, delicate core, ready for the outer coating. The first coating is a layer of milk chocolate. The filled wafers travel along a conveyor through a curtain of tempered chocolate, a process called enrobing. The chocolate is kept at exact temperatures to ensure optimal viscosity and crystallization. Too hot, and it will be too thin and won't set properly. Too cold, and it will be too thick or bloom later on the shelf. The enrobing tunnel applies a uniform coat of chocolate that covers the wafer sphere entirely. Immediately following enrobing, the still wet chocolate is dusted with finely chopped, roasted hazelnut fragments. This is done through a synchronized nut dispenser that sprinkles fragments over the rotating, chocolate-covered spheres. The particles adhere instantly to the tacky surface, forming the crunchy outer texture that defines the Ferrero Rocher bite. From there, the products enter a refrigerated cooling tunnel to crystallize and harden the chocolate coating. This tunnel is kept at a consistent low temperature, typically around 10 to 12 degrees, with humidity controls to ensure shine and stability. Once fully cooled and set, the Ferrero Rochers pass through a final inspection system. High-speed vision cameras scan each sphere for cracks, missing nut fragments, or uneven coatings. Those that fail to meet visual standards are removed automatically by pneumatic diverters. The acceptable pieces then move into one of the most iconic parts of the process: foil wrapping. Ferrero's wrapping process is instantly recognizable. Each sphere is wrapped in a piece of gold foil, folded tightly by high-speed rotary wrapping machines that spin the foil around the product in a process similar to a ballet. The wrapping must be secure but not crumpled, an art that's perfected through decades of machine design and precision calibration. A paper band with the Ferrero Rocher logo is heat-glued around the equator of the foil, acting both as branding and as a seal of authenticity. Wrapped Rochers are then gently placed into brown fluted paper cups, which not only help with presentation, but also protect the spheres from scuffing. Robotic pick-and-place arms transfer the wrapped products into their cups and arrange them into trays or gift boxes. These boxes may contain 3, 12, 24, or even 48 pieces, depending on market and seasonal packaging. Secondary packaging lines group the gift boxes into cartons for shipping. These cartons are automatically assembled, packed, and sealed using robotic case packers. Once completed, the cartons are barcoded, weighed, and stacked onto pallets by robotic palletizers, then stretch wrapped and scanned into inventory. From here, they enter climate-controlled storage warehouses, awaiting shipment to distribution centers around the world. Of course, quality control is continuous throughout the entire process. Every batch of cream filling is lab tested for fat content, viscosity, microbial load, and texture. Wafer shells are tested for brittleness and moisture content. Chocolate is sampled for bloom potential, fat migration, and melting point accuracy. Finished products are subjected to sensory panels who evaluate every aspect of the bite, from crunch to melt to aftertaste. Behind all of this is a digital infrastructure that ties everything together. From syrup cookers to nut roasters to packaging robots, the plant is run by integrated SCADA and MES systems. These systems monitor temperature trends, downtime events, ingredient usage, and traceability data in real time. Each product can be traced back to its lot of hazelnuts, batch of chocolate, and shift team, allowing full accountability and rapid response in case of any deviation. What's more, Ferrero production plants place a strong emphasis on food safety. They are certified to international standards such as ISO 22000 and FSSC 22000, and operate with strict allergen segregation, hygiene zoning, and air filtration systems. Operators wear full protective gear, and certain areas are restricted to minimal human presence to reduce risk of contamination. Sustainability has also become a central pillar of Ferrero's operations. The company has invested heavily in traceable and responsibly sourced hazelnuts and cocoa. Many factories are now equipped with heat recovery systems, water recycling units, and energy-efficient machinery to reduce the environmental impact of confectionery manufacturing. Incredibly, this entire process, from nut to wrapped product, can happen in under 2 hours. That's 2 hours to roast, fill, coat, wrap, and package what looks like a handmade luxury. But it's not magic. It's manufacturing at its most precise. Every movement of every machine, every gram of chocolate, every foil fold is measured, managed, and monitored. The result is consistency across countries and climates. A Ferrero Rocher purchased in Rome will taste the same as one bought in Dubai, Tokyo, or Toronto. That uniformity is achieved not through simplicity, but through complex synchronization across ingredients, machines, and human craftsmanship. From a distance, Ferrero Rocher production might seem effortless, but it's anything but. It's a feat of edible architecture, where layers are stacked with millimeter accuracy, flavors balanced with chemical precision, and every aspect of the product calibrated to evoke delight, bite after bite. In a world of mass production, Ferrero has mastered the art of small indulgences at scale. Each gold-wrapped sphere is a symbol of how far food science and industrial artistry can go, not just to make chocolate, but to make joy. For over a century, Hershey's has been America's chocolate. With its iconic square segments, sweet creamy flavor, and unmistakable aroma, the Hershey's milk chocolate bar has become a symbol of comfort and nostalgia. But few realize how many complex steps, both agricultural and industrial, go into creating each one of those neatly molded rectangles. From cocoa plantations to high-tech factories in Pennsylvania and beyond, the making of a Hershey's bar is a feat of logistics, chemistry, and precision food engineering. It all begins thousands of miles away from the factory floor, in the equatorial regions where cocoa trees thrive. Theobroma cacao, the tree that produces cocoa pods, is cultivated in countries like Ghana, Côte d'Ivoire, and Ecuador. Each pod contains 20 to 40 cocoa beans encased in a sweet pulp. After harvesting, farmers ferment the beans under banana leaves or in wooden boxes for several days. This natural process transforms the bitter, raw seed into a flavor precursor for chocolate, deepening its complexity. The fermented beans are then sun-dried, bagged, and shipped by container vessels to Hershey's processing facilities. Upon arrival, the beans are cleaned to remove debris and sorted by origin, size, and quality. Each origin brings its own flavor profile. Ghanaian beans offer classic cocoa depth, while Ecuadorian beans may bring floral or fruity notes. The blending of these origins is what allows Hershey's to maintain a consistent, recognizable flavor year after year. Once cleaned, the beans enter the roasting drums, massive rotating steel cylinders where they are slowly roasted at controlled temperatures. This step develops the final flavor of the chocolate, similar to roasting coffee beans. Temperature and time vary depending on bean type, but typically range between 120-160 degrees Celsius for up to 45 minutes. As the beans roast, their shells become brittle, and the internal nibs, the part used to make chocolate, develop their signature aroma. The roasted beans are passed through a winnowing machine, which cracks them open and uses airflow to separate the light, papery shells from the heavier nibs. The nibs are now ready to become chocolate. They are ground into a thick, dark brown paste known as chocolate liquor, a 100% cocoa mass that contains both cocoa solids and cocoa butter. Despite the name, there is no alcohol in this liquor, just pure ground cocoa nib. From here, the real engineering begins. The chocolate liquor is combined with milk powder, sugar, and additional cocoa butter in large mixing tanks. The exact formula is proprietary, but we know Hershey's is famous for its milk-forward flavor and slightly tangy finish. That tang is believed to come from a special milk treatment process developed by Milton Hershey himself, involving controlled lipolysis. Essentially, the development of specific flavor compounds by partially breaking down milk fats under heat. Once the ingredients are mixed into a coarse paste, the mass is sent to 5-roll refiners, large steel roller mills that gradually grind the chocolate mixture down to a particle size of roughly 20 microns. This microscopic consistency is what gives chocolate its velvety texture. If the particles are too large, the chocolate feels gritty. Too small, and it may clump or fail to release flavor properly. Each roll in the refiner is set with increasing tightness to achieve a uniform grind. After refining, the chocolate is still dry and powdery. To transform it into a smooth liquid, it enters the conch, a key piece of equipment in chocolate making. The conch is a heated, agitating chamber where the chocolate mass is kneaded for hours. This process drives off residual moisture and undesirable volatiles, improves mouthfeel, and develops the final flavor. During this stage, emulsifiers such as soy lecithin are added to improve flow properties. Once conched to specification, the chocolate is ready for tempering. This critical step aligns the fat crystals in the cocoa butter to ensure a stable, glossy, and snappy final product. Tempering involves a carefully timed series of heating and cooling cycles, typically heating the chocolate to around 45 degrees Celsius, cooling it to 27 degrees Celsius, then slightly reheating to working temperature at about 31 degrees Celsius. This allows the formation of type 5 fat crystals, which give chocolate its desirable characteristics. Now tempered, the liquid chocolate is ready for depositing. It flows into stainless steel depositors, which dispense precise volumes of chocolate into bar molds. Each mold is preheated slightly to prevent premature crystallization and is vibrated to remove air bubbles and level the chocolate surface. Once filled, the molds enter a cooling tunnel, a refrigerated chamber where the chocolate solidifies into its familiar form. After cooling, the molded bars are ejected from the molds by gentle air pressure or mechanical release. Each bar is then conveyed to a high-speed wrapping line. For the classic Hershey's milk chocolate bar, this involves two layers, an inner foil or paper liner and an outer printed sleeve. Wrapping machines fold and seal the bars at speeds of hundreds per minute using heat sealing and cold gluing methods. Each bar is also inkjet printed with a production code for traceability and inventory control. Wrapped bars are then counted, stacked, and loaded into cartoning machines for retail multi-packs or into larger cases for warehouse distribution. Robotic arms and conveyors carry the cartons to palletizers, which arrange them onto pallets in precise patterns. Pallets are stretch-wrapped, labeled, and scanned into warehouse inventory systems. Throughout the entire process, quality control is constant and rigorous. Samples from every batch are tested for fat content, sugar ratio, particle size, flavor, aroma, and shelf stability. Sensory panels perform taste tests to ensure the product matches Hershey's official flavor profile. Microbial testing ensures food safety, and all data is logged in digital batch records to ensure traceability and compliance with food safety standards like SQF, ISO 22000, and FDA regulations. Inside the factory, automation is central. From ingredient dosing and temperature control to tank agitation and mold handling, programmable logic controllers and SCADA systems monitor every parameter. Touchscreen panels give operators live insight into flow rates, cooling curve progress, and downtime tracking. These data streams not only keep the line running smoothly, but also help predict maintenance needs and optimize energy efficiency. Another remarkable component of Hershey's production is its environmental stewardship. Modern facilities recycle water used in cooling circuits, reclaim heat from conching motors, and repurpose off-spec chocolate by reworking it into other products. The cocoa shells removed during winnowing are even used as fertilizer or animal feed, reducing waste. Supply chain transparency is also part of the modern Hershey's commitment. Cocoa beans are increasingly sourced through certified sustainable programs, with investments in farmer education and ethical labor practices. Blockchain-based platforms now allow for bean-to-bar tracking, helping ensure that every bar supports both quality and responsible sourcing. Logistically, the bars are shipped to national and international distribution centers using temperature-controlled routes when needed. Warehouses use first-in, first-out inventory systems, and retailers receive shipments in compliance with demand planning forecasts. Each bar, despite traveling thousands of miles and passing through dozens of steps, remains precisely as Hershey intended. Consistent, safe, and perfectly sweet. It's easy to take a chocolate bar for granted, to see it only as a snack or a treat. But what lies behind that silver and brown wrapper is a world-class production system that balances food science, mechanical engineering, flavor chemistry, and sustainable agriculture. From cocoa farms to Pennsylvania steel, from sugar silos to foil stampers, the making of a Hershey's bar is not just about chocolate. It's about heritage, process control, innovation, and the relentless pursuit of consistency in a product that's been enjoyed by generations. In every square, you taste more than just sugar and cocoa. You taste a supply chain running like clockwork, a formula calibrated to microns, and a commitment to quality that's lasted over 100 years. A Hershey's bar isn't just made, it's built, layer by layer, process by process, from the ground up. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal, high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operation system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand-stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sourced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly from the final stage of yeast fermentation. Steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixers are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking, remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem.